Okay, today we'll move completely different direction. We are not going to solve any hierarchy problem or anything. We are going to look at two things. Doublet models. Of course, there are several references for this, but I think one of the most famous one is by Branco. Branco et al. This already has, after the Higgs has been discovered, there has been tremendous interest into Higgs doublet model. Okay, so just look at Branco et al. Physics reports. Then Davidson, Tabor. There are a lot of papers, Philopsis. Okay. So a lot of interesting papers are there. And after the Higgs has been discovered, so there has been tremendous interest in these models. Historically, they were just like, why not? If there is one Higgs, why can't we have one more Higgs? So what happens to the potential, whether we can study it? Okay, why should only one Higgs be responsible for everything? All the mass terms in the standard model, because there could be much more complicated vacuum structure. So you could have a Higgs which is completely responsible for electroweak symmetry breaking, but another Higgs which could be giving masses to the to the particles and so on and so forth. So the basic idea is that add one more Higgs doublet to the standard. Now, how will you add this? You can have choices. Again, whether you are going to add with the same hypercharge or whether you are going to use a different hypercharge and so on. So, okay, let's assume phi 1 is equal to phi plus phi 0. Phi 2 is same hypercharge. Okay. So the standard model Lagrangian, including the Higgs, fermions, gauge bosons, one Higgs, plus we have del mu phi 2 del mu phi 2 minus V of phi 1 phi 2. The potential becomes much more complicated compared to this normal standard model essentially. So the kinetic terms you write down everything, the Eckart couplings and everything. Okay, you can write it down. Okay, and the other place where it changes is the Eckart couplings. So Eckart couplings, let's write it down as separately. I'll come to it in a second actually. I'll come to Eckart couplings in a little bit actually. You have a lot of variety in Eckart couplings. So these are just the kinetic terms, essentially kinetic terms. So we can actually write it down as phi 1. So this is the full standard model. Now let's look at, so you have an additional kinetic term which has the same kinetic term as phi 1. There is nothing which distinguishes this. Okay, so you know that unless you have some symmetry or something to distinguish, you cannot distinguish two particles essentially. Okay, we'll come to that in a second. Now what is V of phi 1 phi 2? Now this is interesting because of its vacuum structure. What happens to the vacuum? So there are several terms. They go under the name lambda 1, lambda 2, lambda 3, lambda 4, lambda 7. Okay, let's write them down. So the first one, m11 square, phi 1 diagonal phi 1 plus m22 square, phi 1 diagonal phi 2 minus m12 square, phi 1 diagonal phi 2 huh? Right. Then you have several quartic terms. So this is the most general quartic potential you can write down with the gauge symmetry. This is just phi 2, phi 1 dagger phi 2. It's only one term, okay? Now in this, okay, you can choose, you have, this is real, 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 real. All the things with HC can be complex, all these other couplings. Okay, lambda 5, lambda 6, lambda 7, they could be complex. So this is the most general, okay, this is the most general uh, what do you call, 2 Higgs doublet model potential you can write down. Now this potential is extremely complicated. You just added one more 2 Higgs doublet, but that itself makes the potential extremely complicated. The most general form of meaning analysis of this potential is not known. Meaning all possible vacua, all possible places is not completely solved actually. Okay, there are ideas, there are some the people who claim that they had solved it and everything, but it's not, the vacuum structure is not completely solved. Okay, but there are 3 different cases. There are 3 different cases. First case is so-called normal case. In which the vacua are real. So you put phi 1 is equal to 0, v1 by root 2. Phi 2 is equal to 0, v2 by root 2. Second case is much more interesting because you can break Cp spontaneously in a 2 Higgs doublet model. Okay, you know that Cp is broken in standard model. Okay, but the idea is that you can break it spontaneously because you don't want to break it by hand. Okay, it is always associated with some Yukawa couplings, so Yukawa couplings, you know, have complex entries and everything, but if you can generate some spontaneous symmetry breaking associated with some spontaneously, so in this case would be some 0 v1 e power I delta root 2 phi 2 0 v2 e power I sigma. Some such phases will be there essentially. Okay. And the third case is charge breaking cases. Now here you have some beta or something, v1 by root 2, phi 2 some beta prime v2. So that means the charged parts of the Higgses will get to vacuum expectation values. So we want to avoid this anyway. These are not good phases, so you want to avoid this kind of phases in which you don't want the parameters to be such a way that okay. So now let me write down. So in general, what people do is this will also be useful for other purposes, that you avoid, you impose, you reduce the potential. Make sure that there are no, say for example, instead of studying the full generality of all this potential, you remove these 2 terms. Remove these 2 terms by imposing a symmetry called Z2 symmetry. what does it do? It takes phi I to minus phi. Under the imposition that phi I goes to minus phi I, this term is violated, this term is violated. These two terms, you remove them, but this term you keep it because it's dimension full. So you say that it's softly broken Z2 symmetry. You keep this term. Okay. So this term you can see why, because it has only a single phi 2. That's the reason why it violates Z2 symmetry. This one has a single phi 1, so it breaks the symmetry. Okay, the Z2 symmetry. This one has two phi 2s and two phi 1s, so it conserves the Z2 symmetry. Okay. Whereas this one breaks the symmetry, but it has a dimension full term. So it's softly breaking the Z2 symmetry. So then let's worry about this softly broken Z2 symmetry case, and we'll focus on this normal case. We'll forget about spontaneously broken symmetry case. I'll come to that maybe. Let's see.
So this is the maximum reduction that can be done, like even after imposing any symmetry in this generalized potential.
No, this is not the maximum reduction.
It can be reduced more.
So you can play even further actually. Okay, meaning what do you mean by?
I mean that like more lambdas can be reduced, like.
More lambdas. No. This is the maximum. If you want, okay. If you want in terms of lambdas, they were asking.
So like here two constants are now.
Yeah.
Lambdas.
Right. It's true that you have more, meaning two lambdas to be, meaning you can remove them. Now, if you want to remove more lambdas, you have to impose further symmetries. So, it is possible. You start with the two Higgs doublet model, and you can make the what have I'll tell you. You'll get each lambda corresponds to one extra Higgs boson roughly. Okay. So if you have only 5 Higgses, so that's the reason why you keep 5 lambdas. You end up having 5 Higgses and you have 5 lambdas. So you can equate 5 Higgses with 5 lambdas. Now if you keep the standard model lambda and you set all the other lambdas to be very high, or all the other Higgs masses to be very light, so you can remove those also. You can just have standard model like lambda. That's the maximum you can have. The maximum you can have is only standard model. Meaning this maximum reduction you can have. Okay, you can make an effective theory which just gives you standard model, and all the rest of the particles are very heavy. Okay, so that's the maximum thing. There's no indication for a 2 Higgs doublet model to be in nature. Yeah, theoretically you are asking.
Yeah, like suppose if we reduce Z2, so now like the potential is reduced in a way. So if we impose any other symmetry, can potential be reduced more?
Yeah. If you want, how many? Z2 will remove these odd particles, odd terms. Now rest of the terms are all even.
Yeah.
Okay. The only other way you can, there is one more case in which only one of the Higgs gets a wave. The other Higgs doesn't even participate in electroweak interactions.
But then it won't be like two.
Yeah, it is called an inert Higgs model. It's like a standard model, but a doublet, but which is a dark doublet or something essentially, which is inspired by something called twin Higgs models. Okay, so it's called the inert Higgs doublet model, which doesn't participate in gauge interactions, so it doesn't give you masses to the gauge interactions and so on. So if you want, instead of symmetry, if you want to really think in terms of symmetries, actually the full potential term, you have to use something called the orbit theory. Okay, because you won't be able to know all the phases from here. So you re-express all these things in terms of some length variables, either in 4 dimensions or in terms of in 3 dimensions, and then you can write it in terms of some invariants. So the potential will be invariant in terms of some SO3 or plus some SL2C. SL2C is this general Lorentz invariance essentially, plus some larger symmetry essentially. You can write it in terms of some lengths, some combination of lengths essentially. So you take components of this phi. That's how you want to study the vacuum structure. You study in terms of the invariance, in terms of this one essentially, in terms of the lengths, or write everything in terms of some R's essentially, some radius type of things times some potentials. So you can re-express everything, all the in terms of the real components and so on. Because the potential is a real field, right? Essentially. So, but you can do it for the full 7 cases, 7 terms, without imposing the Z2 symmetry. That itself, I had a friend who was a mathematician who was studying those things. Yeah, it's very mathematical. It's nice. Okay, and you can study the phases of the vacuum and everything. So just by adding one more Higgs doublet, the theory becomes super complex actually. Super complex. Yeah. So let's look into this. We will remove these 2 terms, impose the Z2, and really concentrate on the normal. Now the Higgs has, each Higgs has some rho plus I, rho 1 plus I, B plus H plus I pi, say call it sigma I. Phi I. So only, okay, now the point is that, okay, let me just write some perturbations around it, HI. Okay, some HI. So how many degrees of freedom it has? 1, 2, 3, 4 into 2. I is equal to 1 to 2. I is equal to 1 to 2. So it has 8 degrees of freedom. 8 degrees of freedom. Out of which 4 of them are imaginary parts. Okay, and the 4 imaginary part of the 4 imaginary parts. Okay, 4 imaginary parts, 3 of them will become Goldstone bosons. Okay, giving masses to the Z and W. Imaginary components, there are 4 of them. Okay, Then the real components, how many of them are there? 4. So you have here 1 remaining, remainder 1, 0 goes from bosons, 4. Total how many? You'll have 5 physical Higgs bosons. These 5 Higgs small h, capital H, pseudoscalar h plus minus. One charge Higgs, which is a complex Higgs field. Okay. Now let's see what are these 4 masses are essentially. So if this is the case, we can minimize the potential. At the minimum, how do you minimize the potential? The best way is wherever there is a 5, replace it with V1. 5 2, there is a V2. And so write the potential in the minimum.
The Higgs spectrum is similar to that in
MSSM.
MSSM.
But in MSSM, they are highly correlated.
Yeah.
Here, there are 5 independent masses. In MSSM,
It was like Ma plus.
yeah.
minus.
There are all these relations between them. Here, they are independent. I'll just show you the final formulas. Okay, you can see that each lambda corresponds. There is only one lambda in MSSM. That's the reason why they all get correlated. Here, there are 5 lambdas, so you will have 5 independent Higgs masses. Okay, so in the minima, what we have is the relation m11 square. So So you have these two minimization conditions. Now here, now you see the difference between the minimization conditions of 2x development model of the MS system versus 2x development model of the general 2x development model. In the MS system, this was related to the mz square mass because you had gauge couplings. Okay, here they are not there essentially. You don't have any gauge couplings or anything, the minimization conditions. So you can solve them, and then if you solve them, so there are a lot of free parameters, so you can easily solve them actually. So I will write down the formula. I'll write down the final formula for the charge Higgs mass. V square by V1 V2 M12 square minus V1 V2 lambda 4 plus lambda 5. Ma square V1 square plus V2 square M12 square V1 V2 minus lambda 5. So these are the easier ones. Charge Higgs pseudoscalar. So 3 degrees. So the last one would be, what is the mass for the neutral scalar Higgs? So the neutral scalar Higgs is given by some complicated relation. I'll tell you what is beta minus alpha. I'll tell you what is lambda cap and what is lambda. And heavy Higgs so this beta minus alpha appears all the time in the neutral Higgs formula, in its couplings and everywhere. Now beta is defined by tan beta is equal to V2 minus V1, and alpha is the angle which diagonalizes the neutral Higgs mass matrix. Alpha diagonalizes the neutral 2 by 2 neutral Higgs mass matrix. Now what is lambda? Lambda is short form for, again, lambda 1 cos power 4 beta lambda 2 sine square of beta plus 1 by 2 lambda 3 4 5 sine square 2 beta. This is, so the basic idea is that instead of, the mass matrix is easier to see. Okay, the mass matrix is easier to see, but it is complicated because it's not in such a nice format as in MSSM essentially. So lambda cap is also one more function, sine 2 beta lambda 1 cos square beta minus lambda 2 sine square beta minus lambda 3 4 5 cos 2 beta. So you have this 5 Higgses with eigenvalues given by this particular fraction. Now what happens when beta minus alpha is equal to pi by 2? This term vanishes. So you only have this term essentially. So this limit pi by 2 when this term vanishes in the light Higgs is called the alignment limit. Okay? Okay, the eigenvalues are not a problem. We'll see the couplings essentially. I hope I brought the couplings. I'll tell it. I'll check it. I'll write it down in a minute. We will do the couplings in a second. Okay. So beta minus alpha is something called the alignment limit, where beta minus alpha is very close to pi by 2. Okay. So it turns out if you write down the couplings and everything, the couplings, if you want them to be like standard model, then beta minus alpha should be equivalent to pi by 2. So that's called the alignment limit.
Beta minus alpha is pi by 2, then what happens to this heavy Higgs mass?
No, it is finite still because it's not infinite or something like that. Essentially. It should be not exactly equal to pi by 2, but very close to pi by 2. Essentially. Yeah.
So it will be heavier, very heavy.
It pushes it essentially. It also, this pi by 2 also satisfies the rho problem essentially. The rho yesterday we saw the rho could be a problem, right? So it also satisfies the rho, the masses of the rho's and everything. Okay, the rho problem. Now these 4, you see there are 4 parameters here, there are 4 masses here, and there are 4 lambdas, at least 5 lambdas are there. So you can, and m2 1 square. So you can interchange the masses, you can re-express, okay, the masses in terms of lambdas, lambdas in terms of the masses. So you can take these lambdas to be free parameters essentially. Okay, the masses to be really the free parameters, and they in turn fix you the lambdas. Okay, you run the masses and then they fix you the lambdas. So typically in the phenomenological analysis, that's what you do. You take the masses to be free parameters, and then you check whether they satisfy all the conditions on the potential, whether they give you the correct eigenvalues and everything. So that's how you check. All the lambdas to be correct or not. Now, if you study the kinetic terms, so here there are phi 1 and phi 2. The kinetic terms give masses to the Higgs boson, to the gauge couplings essentially. So in the standard model you just have one Higgs, but here you have 2 Higgses. So because the 2 Higgses will mix with each other in the potential, because there are terms which are V1, V2. Now if we just substitute del mu is equal to del mu sorry, and then put it back into this, you would have one mass matrix proportional to G, okay, then, okay, let me write it down. So this is, a med vector. So this is W mu 1, W mu 3, W mu 1 plus I W 2, W mu minus I W 2 minus W mu 3. This is IG, and then we have IG prime Y by 2. Now all this has to be sandwiched between 0 V1 by root 2 and then 0 V1 by root 2. Now it's not just V1 by root 2, you also have V1 H, okay, by root 2, V1 H by root 2. And then here also you have some fields here, xi1 and xi2. So this becomes complicated because you also have the real fields which do not get a vacuum expectation value, but you can have some excitations over 0. You have some excitations over 0. Okay, you have some excitations over 0 essentially. So this mass matrix, you have to, if you want to get the couplings, you have to diagonalize this mass matrix, you have to diagonalize this mass matrix, and so on, so essentially. When you do all that, the Higgs couplings will end up with having something like Higgs WW coupling has a form which is G some form sine beta minus. And the A will have G cos, okay, it will not have anything essentially, okay. The A will not have gauge couplings, especially in the limit when the V's are not complicated, when the V's are not complex. So the Higgs and the pseudoscalar Higgs will not mix in the limit V's are complex essentially, okay. But also, and then you have the Higgs coupling G cos beta minus alpha. And then the charged Higgs, which has the couplings very similar to the W couplings, roughly. Okay, I'm not writing the exact expressions. Somehow, I just brought the somehow I didn't bring them. I thought I brought them, but anyway. So in the limit, this goes to pi by 2. The Higgs coupling will be exactly like in the standard model Higgs. So this has to be forced. So this forcing can be achieved by imposing some symmetries on the Higgs potential essentially, on the Higgs fields actually, in the Lagrangian. So this is called natural alignment mechanism. You want to look for, okay. So you want to look for alignment naturally. Now, so this tells you that the pseudoscalar doesn't have gauge couplings. Now, say suppose now you are looking at Higgs to gamma gamma, Higgs to ZZ, all the data from the lab on LHC essentially. Now Higgs gamma gamma in you know that it's all very close to standard model, so you can fix this all these couplings, bunch of couplings. Pseudoscalar, you don't have found no data on it, but anyway you're safe because it doesn't have any gauge couplings. So the only way you can prove a pseudoscalar is through couplings to the fermions, tau tau, okay, tau data or BB data or something essentially. And these can be proved again by the gauge couplings essentially. They will be not completely vanishing, okay, they will be can be proved again by gauge couplings. But they will be very heavy, at a very heavy level. There are a bunch of theoretical constraints, okay, on the stability of the potential and so on. So all the lambda should be greater than 0. All these conditions, okay.
If these couplings are measured to be exactly a standard model, that means this is in the alignment limit.
It's in the alignment. Right now we know that we are in the alignment limit. We already know actually. So the deviations would be very, very small. Also, it's not just the couplings. The rho parameter also requires they should be in the alignment limit. Okay. So the rho in the 2 Higgs doublet model is mw square by mz square sin beta minus alpha. Okay. So this also should be in the alignment limit essentially. So the rho parameter is also should be in the alignment. It tells you that it should be in the alignment limit. So imposing all the theoretical constraints and everything, you look for what are the regions. Okay. So the theoretical constraints are independent of how the Higgs couples with fermions. So there are a bunch of lambda 1 plus lambda 2 should be greater than 0, so on. So these are all these conditions are there essentially. So these conditions are independent whether how you couple your Higgs to the fermions. But now you have a lot of choice of how to couple the Higgs to the fermions. Okay, because let's remember that the uptype couples differently compared to downtype. In the earliest, one of the earliest papers on 2 Higgs doublet model was by Weinberg and Feinberg. Okay, so what they said, okay, they had some errors in their calculations. Okay, so they had errors in their calculations, but independent of that, they said the first thing you can do is you can couple both the Higgses to all the kinds of fermions. Okay, so you have phi 1 2 yu 1. You have two Higgs couplings, yu 2 qu phi 1 phi 2. Then you have yd 1 qd phi 1, then yd 2 qd phi 2, ye 1 q le phi 1 plus ye 2 le phi 2. Nowadays, this is called type 3 to Higgs doublet model. Type 3 to Higgs doublet model actually. So both the Higgses couple into both the things. Now what happens? Suppose if I diagonalize this is not diagonal. I diagonalize this, I get the CKM, but in the basis where there is a CKM, I also have additional Higgs couplings, which are off diagonal. Even in this basis where this is diagonal, there will be, you cannot simultaneously diagonalize both the Yukawas up type and both the Yukawas which are down type. So you will have in type 3 level flavor changing neutral currents which are not there in standard model. In standard model, all the flavor changing neutral currents come at one loop essentially. Okay, so Weinberg and Feinberg were one of the first essentially to realize this thing, and then they showed that you will have process like muon going to an electron, emits a Higgs and E. So mu to 3E process would happen in this kind of with the Higgs essentially. You'll exchange some Higgs essentially, some Higgs. Okay, you can calculate it and then just show that. This process at the tree level it happens, so its rate is very high. It's not a loop process, it happens at the tree level essentially.
Will be constrained.
It will be highly constrained. So there is Krivelin and Groib have looked at an updated version of this one essentially, up to Higgs doublet models.
So what is alignment without decoupling?
Alignment without decoupling. So you choose beta minus alpha, but the particles need not be heavy. Decoupling requires heaviness. Okay, but Higgs in general is not very decoupling particle. Okay, Higgs is not a very decoupling particle, but is it into Higgs doublet model context you are talking?
Yes. To Higgs doublet or MSSM?
Alignment essentially is that it's like the couplings are such a way that they are like the standard model. Now decoupling is a different question. Decoupling is that they don't know Higgs effects, residual Higgs effects. But you can have scenarios in MSSM as well as here essentially. So there could be some non-decoupling diagrams. Say for example, the one typical example is something called the Bar-Z diagrams. So you heard of this name. So essentially that if you have, these were formed in terms of EDMs essentially. So you have a W, so if you have say muon, some fermion, and then there is a fermionic loop. This loop could be large, it's a two loop diagram, and this is a top loop, say for example. And here you have a Higgs. Now this diagram can be non-decoupling. So even in the limit where the Higgs goes to infinity, you'll have still some effects. It's a two loop effect, but still it will be non-decoupling. Okay, so these kind of scenarios can exist essentially. So typically, if when the Higgs has some couplings essentially, so Higgs effects need not go to zero in the limit Higgs mass goes to infinity. So when Higgs mass goes to infinity, you still have some effects. Those are called non-decoupling effects. Okay. So, but that is very just not in MSSM and Higgs doublet model. If you add singlets or in many models there is non-decoupling. So the decoupling theorem has a lot of exceptions. Okay, the decoupling theorem has a lot of exceptions. In MSSM, you'll have effects in where in the limit, because the Higgs completely doesn't decouple, it will have some effects, residual effects in terms of some tan beta or some, okay, some such scenario, it leaves some effect essentially. It doesn't completely decouple. The amplitude doesn't go to 0 in the limit m Higgs goes to infinity. So that's non-decoupling. So you can have alignment, but in which the heavy Higgs completely don't decouple. So now you have various scenarios. So one most popular one is called type 2. In type 2, up type particles coupled to one Higgs, down type particles coupled to other Higgs. So in type 2, these dotted lines are 0. Okay? Up type coupled to phi 1, down type fermions coupled to phi 2. Then, so in these two cases, you don't have any flavor changing neutral currents. Okay? Then the other one is type 1, in which the quarks couple to the same Higgs. Okay? And the lepton couples to another Higgs. So this box goes to 0, and this kind of box goes to 0.
Both up down will go.
Up down coupled to same Higgs, like in Standard model. If you reverse it, it's called type X. Okay, it's the same thing essentially. There's also something called the type X essentially. So type 2 is like MSSN. So there is tan beta enhancement and everything. Type 1 is very simple, this one essentially. So the couplings are different. So you'll find this table with top, tan beta and what is that enhancement and everything. Okay, but let's just okay. Okay, so type 1 all up and down type and charged electrons coupled to same Higgs. Now there is a variation of the thing, that in which type X, it's opposite essentially, that um, it's only lepton specific. It's called lepton specific. So here, that means lepton is only coupled to the type one particular Higgs, quarks coupled to another Higgs essentially. I'll just write down. Just
So type X is just type 1 reverse.
reverse of the type one. I just I won't show the PDF. I'm not able to download the PDF. Okay. If I have the PDF, then I can show. Here it is. Okay. So how do I show this? Okay. So the couplings, you can divide. There is also something on the type Y. Oh, okay. I should have made some slides or something. Okay. So the couplings all have this form. Okay. So type 1, type 2, type X, type Y. So now you see how the enhancement varies essentially. Okay. Type Y is the reverse of type X. Okay. Type 1, all of them coupled to the same Higgs. Say phi 1. Now if you reverse it, it becomes type Y. Phi 1 to phi 2. Type 1, all of them coupled to the same Higgs, all the echo couplings, but they participate in, it's not inert Higgs doublet model, but it participates in gauge coupling, the breaking of the gauge coupling. Type X, lepton specific, leptons coupled to one Higgs, quarks coupled to another Higgs. Now you reverse this one,
Then it will become type 1.
it will become not type 1, it will become type Y.
Leptons coupled to phi 1 and quarks coupled to
Phi 2. In type 1, all of them coupled to the same Higgs.
Okay, correct.
Okay, it's like in standard model. Type 1 is nothing but standard model. Standard model plus this one. Okay. So you have the various cot beta and all these factors which come here essentially. And the Higgs couplings also you can see essentially. Okay. Now, what is the problem with this model stills? you can escape efficiencies, tree level efficiencies, but loop level efficiencies are also complicated. So one of the biggest problems is B2S gamma. B2S gamma, actually there is a limit derived by Misiak and company. In 2H doublet model, wherever the rule is that wherever there is a W, you replace with the charge Higgs. And that happens exactly like here in type 2. And then this 2H doublet model is the B2S gamma is branching fraction is very well measured, and you also have the exponential limit which is within 5% of the theory. Actually, the exponent is much better compared to theory. Theory has some errors. Okay, the exponent is much better actually, and the theory has been computed at 4 loops orders by Messier company
In standard model.
in the standard model. And now you can use that. So within the error bars, it should lie the B2S gamma essentially. So you can use it to constrain the mass of the charge Higgs, and the charge Higgs already has a limit. Mass of the charge Higgs should be more than 450 GeV or something, roughly around half a TeV. Okay, so this puts strong constraints on type 2 and type Y and type Y. Okay, type 5 and type 2 have very strong constraints on B2S gamma. Type 5 is like a down type quarks also coupled with the lepton. It's like reverse of this one, somewhat like reverse of this one. Okay, like I'll show you again. It's so the down type has a tan bit enhancement in type 2 and type Y. Down type has a tan bit enhancement in type 2 and type 5. Okay, so due to the tan bit enhancement, they are completely ruled out. You can also have, I'll send you the PDF. Okay, I'll put it. Okay, anyway. So then this is one constraint on 2H doublet model. But then why 2H doublet models are interesting nowadays? Because of G minus 2. Okay, so one of the oldest papers on G minus 2 contribution was done by Weinstein and other people, lot of other people, not just Weinstein actually. So in G minus 2 what happens is that you can have a Higgs contribution, and this can be large if the Higgs is, mass of the Higgs, neutral Higgs is less than 5 GeV. Okay, so the one loop contribution is very, very small essentially. So because the Higgs mass is greater than 5 GeV, it is completely ruled out. But the two loop contribution contains, here again your bar Z will come. All kinds of diagrams, including bar Z diagrams. Two loop contribution can be large. Okay, can be large. And but this requires an MA if you put in 60 GeV. So the pseudoscalar mass is very, very light. So that is the hunt. The last few years was a hunt for pseudoscalar in colliders, which is very light, and using the tau data and so on. So Now, other than G minus 2, so this G minus 2 rules out if you put in all the constraints and everything, type 2 and type Y, and only type X is allowed. If you want to solve the G minus 2 problem, only type X is allowed essentially. Okay, so that became the hunt for type X essentially. So you are looking for type X like 2x doublet models. Then why is 2x doublet models are interesting? There are two more things. Is whether you have criticality in 2x doublet. This is not explored well in great detail actually. Some RG running is used. People right now are doing phenomenological fits, but theoretically also, in terms of criticality, what Jan Judice was talking about in standard model, you can ask the same questions. What happens whether all the lambdas will be greater than or equal to 0 all the way up to Planck scale. So this is explored a little bit, but I don't know if people have looked at it in greater detail actually. So some analysis has been done, but this has not been studied. The criticality aspect has not been studied essentially. Whether there is actually a 0-like scenario, whether there is a metastable region or not. Another thing which could be interesting in 2x doublet model is electroweak first order phase transition. Right now, most of the interest is in collider signatures and solving the G minus 2 and whether you can do it. Okay. But there are two other important, whether the criticality of the 2x doublet model is valid or not, and whether you can have first order electroweak phase transition. What is first order phase transition? I told you that in the class sometime that Vc by Tc should be greater than 1. And if you take a finite temperature one loop effective potential, okay, Vc by Tc should be greater than 1, the critical temperature, and you should have first order phase transition. Because gut baryogenesis doesn't work, so you need a phase transition at first order, at electroweak scale. So this leads to baryogenesis, but in the standard model, this has a constraint that the Higgs mass should be less than 60 GeV. So first order transition is violated in standard model. What happens in 2x doublet mode? And 2x doublet mode also has CP violation, spontaneous CP violation. Okay, so people are looking at getting first order. So it is possible. There are regions of the parameter space where first order phase transition is actually possible in 2x doublet model. But combine with, because these calculations are so complicated numerically and also, to combine it with also spontaneous CP violation would be actually a good thing to look at. But these are hard calculations essentially. Okay. So yeah, so 2x doublet models have become extremely popular in the recent times. Actually, there are a lot of papers, some 200, 300 papers in the last 2-3 years, I think, essentially. So mainly because to look for a pseudoscalar or for a charged Higgs, okay, or a heavy neutral Higgs essentially, and whether they can be still consistent. So because there is a chance to rule them out, meaning or to put a very strong constraints as the LHC is running, so these are becoming very, very interesting actually. Already the type X model has a very, very thin line which is still allowed. Most of the region of the parameter space is ruled out by LHC from tau data actually. So if the fermionic couplings becoming better, the 2 doublet model can be actually be ruled out, or a G minus 2 solution can actually be ruled out by 2 doublet of 2 doublet. Okay. So of course now you can say, okay, I'll allow lambda 6, I'll allow lambda 7 and then see if something can be changed and everything. one can play the game, but yeah, in general, it's not going to be easy. You can have some definitive statements in the next few years by the end of run 3 about 2 Higgs doublet model essentially. So that's the reason why it's interesting. Okay. Yeah.
People are basically looking at G minus 2 right now. Like
Right now, most of the focus is on G minus 2. G minus 2 and tau data, so pseudoscalar data essentially. With various options, and yeah, that's the main thing. Okay. So what do you want me to tell tomorrow? Should I take a lecture or no? Okay. Should I talk about twin Higgs or something? What do you want to listen? I cannot cover composite Higgs. Composite Higgs, it's a lot of work because I need to start with chiral perturbation, current theories and everything.
Some current status like
On
these models and whatever we have learned.
okay,
Some like what has been ruled out and
okay,
the experiments.
okay. On I can yeah, something I can do. I'll try to cook something. Yeah, that will be a lot of work for me, but I'll do. I'll see something actually. Yeah. But these are interesting actually. Next week, I think 17th or something, 2 weeks from now, Devtosh will come. I don't know what he'll talk about, but he has looked at say the RG running issues, criticality, and stuff like that. So one can ask him if he's still working on it or something. Okay, one can talk to him. That could be interesting actually. Whether the criticality issues have been looked at in 2 Higgs doublet model actually. But now we have some analytical calculation techniques for potentials, meaning tunneling effect, essentially for the tunneling effect. Okay, so one can ask whether you can use those tunneling effects in 2 Higgs doublet models and see what happens, what is the situation, the lifetime of the vacuum, because none of these analysis actually put the lifetime of the vacuum clearly, meaning they don't do, because as I said, the potential is so complicated and everything. Okay, it's a multi-field potential, so it is just too complicated. Okay, so I'll stop now, and tomorrow I'll say some generic things.